My name is Charles Gammie. I'm from University of Illinois, and my assignment is to talk about black hole accretion. So before we start in, I wanted to start with just a brief discussion of characteristic scales for talking about black holes, because I know some of you work on this, and others of you have very different backgrounds. Um, so the first important scale is a characteristic length scale, the gravitational scale, which is just gm over c squared, where m is the mass of the black hole. And this is 1.48 kilometers for a solar mass black hole, and 1 AU for a 10 to the 8 solar mass black hole. Okay, and the characteristic time scale associated with that is just the light crossing time for the gravitational radius, and that's gm over c cubed. And this is 4.9 microseconds for a solar mass black hole, and about 8 minutes for a 10 to the 8 solar mass black hole. Okay, so these are the fundamental scales of the system. The inner regions of accretion flows onto black holes have this kind of length scale, and they change on this kind of time scale. And that's important because, as we'll see, most of the energy in these accreting black holes is emitted, most of the radiant energy is emitted close to the event horizon. Okay, we also want a characteristic scale for the accretion rate, m dot, grams per second, the rate at which material is falling into a black hole. And I think most of you learned at your mother's knee what the Eddington luminosity is, but let me just say this so that we're all on the same page. The idea is to find first a luminosity where the radiative force on a hydrogen, a proton, and an electron is equal to the gravitational force. So the gravitational force is this. So again, this is the mass of the black hole. This is a proton mass, and we're sitting at a radius r away from the black hole. And we want to calculate what the force is on a single electron that's associated with this proton. And they're understood to be sort of bound together by electrostatic forces. So this is the energy per unit area. We can convert this into a momentum flux per unit area by dividing by c. And then we can say how much of this is intercepted by the electron by multiplying by the Thomson cross-section. So you'll see, as Eddington did, that the radius cancels out, and then we can solve for a characteristic luminosity, and that gives us C MP over sigma t, which is a little over 30,000 solar luminosities for a 1 solar mass black hole. Okay, so in this business, people speak of the ratio of the luminosity of a source to the Eddington. Luminosity is the Eddington ratio. But we're interested in building physical models, so we want to talk about characteristic accretion rates. And there's a notion that when a gram of matter accretes, some fraction of its rest mass energy is released as radiant energy. And that fraction is called the accretion efficiency. And to convert this m dot to a characteristic Eddington accretion rate, what we do is define a typical efficiency of accretion. So we say the luminosity is equal to m dot c squared times a characteristic efficiency, and everybody in this business uses 0.1 for the characteristic efficiency. So that gives us m dot Eddington, which is equal to L Eddington over epsilon c squared, where for the most part, people assume that the characteristic efficiency is 0.1, even if in the particular system we're studying, it's not radiating with an efficiency of 0.1. Okay, so this is equal to 2.2 solar masses per year for a 10 to the 8 solar mass black hole. And you can see immediately that this also implies a characteristic timescale for changing the characteristics of the black hole, which is just this. It's known as the Salpeter timescale. And it's just the mass divided by the Eddington accretion rate. And you can work this out. This is the same for all black holes, 4.5 times 10 to the 8 years times the efficiency. Okay. So there are the characteristic scales, fundamental characteristic scales. We can also make some estimates immediately of conditions around an accreting black hole by assuming that the, yeah, did you have a?
Why is that epsilon set to 0.1?
Yeah, I'm going to get to that actually. But in short, the classic estimate for the accretion efficiency of a black hole says that matter comes down from far from the black hole and spirals in gradually through a series of nearly circular orbits, and then winds up on what's known as the innermost stable circular orbit. And the location of that innermost stable circular orbit and the energy of a particle on that orbit are a property of the metric. And you simply assume that all of the energy required that you had to get rid of to get from infinity down to that circular orbit has been radiated away. And that allows you to calculate an efficiency, and it's sort of 6-7% for a non-rotating black hole, so-called Schwarzschild black hole, and up to 42% for a maximally rotating black hole. Okay, there's also observational evidence that black holes accrete with a typical efficiency of about 0.1. But I think that's a little dodgier. Is this being broadcast? Okay. Okay, so now let's think about what would happen if we had material falling into the black hole in sort of a spherical way. So we're going to say the accretion rate is something like the surface area of the black hole, which is of order 4 pi Rg squared. Okay, I'm neglecting lots of factors here that would change this by up to pi cubed. Okay, so 4 pi Rg squared times the density times characteristic velocity for infall close to the event horizon of a black hole. Okay, so this is just the mass flux integrated over the surface of the black hole. So I can use this to estimate a characteristic density close to the black hole and express that in terms of the ratio of the accretion rate to the Eddington rate. Okay, so so this implies a characteristic density, which is of order m dot over 4 pi Rg squared c, which is, okay, so this means 1.7 times 10 to the minus 12. 1.7 10 to the minus 12 m dot. Okay, so this little m dot means the ratio of the accretion rate to the Eddington rate times the mass in units of 10 to the 8 solar masses to the -1. Okay, so this is a characteristic density. You can turn this into a characteristic number density if you remember that the mass of a proton is about 10 to the -24 grams. So this implies a number density of order 10 to the 12. Okay, we can also estimate a characteristic temperature. And the characteristic temperature is just the virial temperature around the black hole. So the virial temperature says 2 times the kinetic energy of a particle plus the potential energy is equal to 0. And so I can get a characteristic temperature from this. And that temperature is the rest mass energy of the proton divided by 3K. Okay, and this is of order 3.6 10 to the 12K. All right, and finally, so this is my last really crude estimate for now, is an estimate of the characteristic magnetic field strength. And so we can get that by getting the gas pressure from this density and temperature, assume it's an ideal gas, and then set that equal to the magnetic pressure, which is b squared over 8 pi. So to get B characteristic, we take b squared over 8 pi, and we set this equal to rho k T characteristic over the mean molecular weight, which we'll just take to be the half the proton mass. So we can solve this, and this gives us 1.1 times 10 to the 5 Gauss times m dot to the 1/2 ma to the -1/2. So starting from basically nothing, we have got characteristic density, temperature, and magnetic field strength scales for close to the black hole. Yeah. Yeah, so I would say it's a common assumption in astrophysics, but I also think that there's some evidence from numerical simulations of these systems that you tend to reach sort of equipartition field strength.
So that would be equipartition with the kinetic
With
energy, which assuming virial equilibrium would be the same. But
yeah, so I can go into this. So let's suppose we have an accretion disk, which is orbiting the black hole, and we have magnetic field in the accretion disk, and we start to turn up the field strength. When this field strength is exceeded, field begins to escape rapidly from the accretion disk. It bubbles up out of the accretion disk. Now, there are a lot of exceptions to this argument, so I don't want to push it too strongly, but the idea is that the dynamo saturates at this sort of level in accretion disks. It's not a rigorous statement.
I mean, in the sun, that would
Yes.
really not work, right? Because magnetic buoyancy occurs way earlier.
Yes, I understand. I just think the dynamics are different in accretion disks. Yeah. Yeah. Okay. All right. So here's the outline. of what I'll talk about. And I've done the fundamental scales, and now I just want to talk a little bit about astrophysical motivation, talk about the Kerr metric a little bit, go on to the sort of set of classical accretion models, which I have to talk about. I don't really want to talk about them, but they're so deeply embedded in the way people talk about black hole accretion that we have to cover it. And then I'll talk about numerical models, the Blanford-Znayak effect, and some open questions. Okay, so astrophysical motivation, which accreting black holes are we interested in? There are lots of examples of accreting black holes, including in probably in gamma ray bursts. I'm going to restrict discussion to galactic nuclei and stellar mass black holes. This object here is NGC 1068, which is a prototypical or archetypal Seyfert-2 class active galactic nucleus. So Seyfert-2 means that there's an accreting black hole in the middle, but we probably see it edge on with the actual inner accretion flow obscured by a dusty torus that's orbiting the black hole. And this object has played an outsized role in the history of thinking about these Seyfert-2 systems because it was is the cornerstone of the argument for a so-called unified model of active galactic nuclei. So in the unified model, Seyfert-1s are seen face on and Seyfert-2s are seen more nearly edge on. And part of the argument that we're seeing this edge on is that in polarized light, one can see the broad lines characteristic of the inner parts of the accretion flow. And it's believed that those polarized broad lines arise from light that's generated close to the black hole and then scatters off electrons that are sitting over the poles of the accretion flow. So this is a famous old argument. I want to mention one other thing about this system, which is that the galaxy and the disk are probably inclined at slightly different angles. And I think starting in on this, most of us probably had starting in on thinking about black hole accretion flows, most of us probably had the idea that, the disk in the center of the galaxy is probably oriented in the same way as the rest of the galaxy. And that is generally not true, or at least there's pretty strong evidence that that's not true, both from systems where we can directly observe a disk in a molecular line orbiting the central black hole, and in cases where there's a jet which we think is emerging perpendicular to the inner accretion disk, we know that the jets do not in general line up with major or minor axis of the parent galaxies. So something's going on here that decouples the orientation of the inner accretion flow from the galaxy. Yeah. Um, maybe one could construct an argument like that, but let me give you an example of our galaxy. Now, we don't know exactly what the orientation of the inner accretion disk is in our galaxy, but there's people associated with the gravity experiment who believe that the disk is actually oriented face on. And we have not experienced a very recent major merger. Okay, so speaking of the galactic center, oh, by the way, this is probably a 10 to the 7 solar mass black hole, accreting it close to the Eddington limit, so m dot of around 1. I'm going to use up all my time on this stuff. So this is an ESO propaganda video of about the galactic center. It zooms in from a big piece of the sky, moving through different wavelengths, starting in the optical and then moving into the infrared, so that one can ultimately see individual stars orbiting around the black hole in the center of our galaxy. So this is work that's associated with Reinhard Genzel and company at MPE, and Andrea Gay's and company out at UCLA. There's intense competition between these two groups. Okay, by tracking these individual stars, it's possible to deduce quite accurately what the mass and distance to the black hole in the center of our galaxy is. And those are now known to better than 1% thanks to the gravity experiment. Okay, so our galactic center black hole is small. So it's around 4 × 10⁶ solar masses, and it's probably accreting at around 10⁻⁸ of the Eddington rate. So it's an extremely underluminous galactic nucleus. Okay, this is my theorist map of the center of the galaxy that's designed to give you a sense for just how many orders of magnitude and scale we have available to change the orientation of the gas, as you asked about, in between the large scale that we observe and small scales of around gm/c², close to the central black hole. So this is a map of our galaxy. Central black hole is here. New York City is here. And this shows distance from the center of the galaxy in units of gm/c². So we're out at about 4 × 10⁻⁻ gm/c². Okay, so that means that to resolve the gravitational radius in the center of the galaxy, we need a resolution of 1/410⁻⁻10 radians, or thereabouts. Okay, so this gives the angular scale of each of these things in units of milliarcseconds, arcseconds, and degrees. And then this is in physical units here. Okay, so there's a lot going on as one gets down toward the black hole in the center of our galaxy that we know about because we're close by and we can resolve these things much better than we can in external galaxies. So for example, those stars that I just showed you, which are resolved thanks to infrared adaptive optics on Keck and VLT, are out here at around 10⁴ gm/c². The Bondi radius, which I'll get to shortly, is out here at a few 10⁵. And then there's a lot of junk around. So in particular, I want to point out this thing, which is so-called central molecular zone. So off on one side of the center of our galaxy is a molecular cloud with a mass of about 10⁷ solar masses. So we have 10⁷ solar masses of molecular hydrogen just sitting there with, a mass that exceeds the mass of the central black hole by a factor of a few. So this molecular cloud is probably orbiting in the galactic bar, and someday it'll pass close to the central black hole, and there will be a lot of excitement. Okay, so this is overview of our galaxy, low accretion rate black hole, relatively low mass for a galactic nucleus. Okay, the other example here, which I have to talk about, is M87. So this shows a famous HST image of the galaxy M87. It has about a 6 billion solar mass black hole in the middle, and it has this prominent blue jet coming out of the center, which was discovered 101 years ago, and has a scale of order 10⁶.5 gm/c². Okay, and as some of you know, EHT was recently able to resolve the inner accretion flow here, and that produced this sort of orange bagel image, which shows the accretion flow on scales of around 10 gm/c². Okay, and again, to give you a sense of the range of scales, I have another European Research Commission propaganda video. This zooms in from ALMA to M87. This is flickering a bit. Okay, so this first shows the low frequency radio halo of M87, and then zooms in through a progression of steadily higher frequencies to look at the jet on smaller and smaller scales. So you can see VLBI has been making its way down to the smallest scale over many decades. All right, so another example of an accreting black hole. This one has a much higher mass, 6×10⁹ solar masses, and it's accreting, we think, at about 10⁻⁵ of Eddington. Okay, so I don't want to leave out the stellar mass black holes. This is a famous old image of a set of accreting stellar mass black holes in our galaxy. We see these black holes because they're in binary systems, and their companion is an ordinary star that's losing mass, and the black hole is capturing this mass and then radiating as the plasma accretes onto the black hole. I want to draw your attention to one of these guys, GRS 1915, which is one of the most studied examples. So this is around a 12 solar mass black hole, and it's not accreting in a steady fashion. So it exhibits all kinds of interesting behavior. So I'll show you a light curve, an X-ray light curve from Rossi X-ray Timing Explorer. So you can see that there is periodic behavior here in the X-ray emission, which we think is coming from very close to the black hole. And there's some kind of structure here which we ought to be able to explain with a good theory of black hole accretion. But unfortunately, it doesn't just do this. It also does this. And this is really the stuff that nightmares are made of. So there's a whole spectrum of so-called quasi-periodic oscillations in these sources. Some of them people have attempted to identify with characteristic orbital frequencies close to the black hole. Others probably have to do with precession of a tilted disk. But I would say that there are no ab initio models of these so-called quasi-periodic oscillations that are well justified. Again, I'm going to get in trouble if anybody cares to watch. Okay, so this is a 12 solar mass black hole. Sometimes it's accreting far below Eddington. Sometimes it's accreting very close to Eddington. Yeah.
Firmly educating myself. The neutron star objects, there are, as you know, some models which try to explain the quasi-periodic oscillations. Are you saying, of course, the mechanisms there are rather different, crystal coupling to MHD and so on and so forth. No such things exist for black hole QPOs?
Well, there are lots of models. Yeah.
But I just heard you say that there are no good models. Perhaps
I did say that. Both those are true. So it's not that they're, I mean, I don't want to, unduly trash a lot of work, but there are around 100 models. I think there's a review paper by Ron Remillard, which produces a nice table of papers and describes each of the models. Some of them are very poorly justified. Some of them are better justified and have to do with frequencies of orbits in the space-time. But none of them are really ab initio in the sense that they look at the dynamics of plasma close to the black hole and then have a well-founded way of translating variations in the plasma into variations in the light curve. So that's, at the end, I have an open questions list, and this is, I think, one of the outstanding open questions in the field. Yeah. Right. Okay. So the bins are 1 second in both cases. Yep. So 10 solar mass black holes. So the characteristic time scale close to the event horizon is around 10 microseconds. Yeah. Okay. Okay. On to the Kerr metric. So I want to spend a little time talking about Kerr. And rather than write this on the board, I'm just going to put it up. Lewis gave a very nice talk about this, some aspects of the Kerr metric, including something called ingoing Eddington-Finkelstein coordinates. Last time. So what is the Kerr metric? The Kerr metric is a vacuum solution to Einstein's equation with axial symmetry, no charge, and it's characterized by two numbers, a mass and an angular momentum. And the angular momentum is usually recast in terms of something called A star, which is angular momentum divided by characteristic angular momentum, which is just mass times rg times c. And this is dimensionless. And the practice in the relativity community is to use this to indicate something with dimensions of m, and to use A star to indicate something that's dimensionless. But astrophysicists are typically not dealing with black holes that are changing their mass very rapidly. And so I'm going to get a little sloppy and use these two things interchangeably. And in fact, this is the A that appears up in those equations. Okay, so this number, it's a feature of the Kerr metric that this number varies between -1 and 1. And for spin outside this range, there's a naked singularity, and we really don't know what to do with that. There are a lot of reasons for not even considering those models, including the fact that they seem to be unstable. Okay, so we're thinking about a specific range in spin. So I've written down the metric up here. This is the G mu nu that appears in this expression. So this is the invariant interval. This is something that's related to the separation between two points in space-time, and it's a coordinate invariant. So we can write this down in any coordinate system and get the same answer between two events in space-time. Okay, so another thing I want to point out about this metric is that this term, which is the GTT term in both these coordinate systems in which I've written the metric, is the one that governs the Newtonian dynamics. So GTT is near the Newtonian limit 1 minus 2 phi over c squared, where phi is the Newtonian potential, not a coordinate. Okay. Okay, and then just to help you, you'll remember that this metric can appear with indices up or down. One matrix is the inverse of the other. And I also want to mention the 4 velocity. Okay, the forward velocity is the rate of change of coordinates according to a clock that's carried by an observer moving with that forward velocity. Okay, so that's that clock is so-called proper time. And usually denoted by tau. Okay, so just to remind you, in Minkowski space, in Cartesian coordinates, this becomes u mu is equal to gamma vi, where gamma is the Lorentz factor. So and v is the 3 velocity in each direction. Okay, okay. And then again in Minkowski space, u mu is minus gamma vi. Okay, so the metric that I've used okay, so I use the metric to raise and lower indices, and this metric in Minkowski space and Cartesian coordinates is diagonal, and it's minus 1, 1, 1, 1. Okay. Okay, this is all motherhood and apple pie, right? Okay. The next important feature of the forward velocity is that it's normalized this way. So u mu is minus 1. Okay. And you can think of this as sort of a definition of proper time. But if you know I do this calculation, this gives me, based on these two, Minkowski space and Cartesian coordinates, I get minus gamma squared plus gamma squared v squared. And that tells me that gamma squared is equal to 1 over 1 minus v squared. So it's also sort of a definition of the Lorentz factor. Okay. This is the forward velocity for a particle with mass, but we can also think about the motion of photons in the Kerr metric and or in any metric, and we usually denote that using k, and that's dx mu d lambda. So this is the rate of change of coordinates with respect to some affine parameter that defines that's defined all the way along the ray. And one way you can think of this affine parameter is as something like ds over the frequency. Okay, so it's some kind of frequency scaled change in length. But each of these things are this thing. I have to be careful about using ds because I used it up there, but this is a frame-dependent quantity, and this is a frame-dependent quantity. Okay. All right, so so this thing in Minkowski, in Cartesian coordinates, goes to minus omega ki, where k is the 3 vector, wave vector associated with a photon. And each of these things obeys a separate normalization condition or separate constraint, which is k mu is equal to 0. So these are called null geodesics, okay? And if you work out what this means in Minkowski coordinates, this Minkowski space and Cartesian coordinates, this implies minus omega squared plus k squared is equal to 0. So it's the dispersion relation for photons. Okay, that's what the null condition means. Okay, so it's also a property of these metrics that they satisfy Einstein's equations. And I've given you, or I will give you, some Mathematica scripts in the material for the summer school where you can actually just check this yourself. Okay, so that means that because this is a vacuum solution, that's equivalent to R mu nu is 0, where R mu nu is a quantity that is related to second derivatives of the metric. So it's sort of second derivatives of the potential is equal to 0. So it's sort of Poisson equation, or a variant, an elaborate variant on Poisson. Okay. Next topic is the equation of motion. So I think I'm going to get all this done before lunch. So I don't know if any of you have read about this, but there was a study done of Israeli judges who were reviewing parole applications. And it was discovered that if you went up for parole early in the morning after people had just had breakfast, then you were far more likely to get parole than if you went up right before lunch when people were hungry. Okay. All right, so equation of motion, we know that for a massive particle, dx mu d tau is equal to, is equal to u mu, and d mu mu d tau is equal to minus gamma mu nu lambda u nu u lambda. Okay, so this thing is the connection, or Christoffel symbol in a coordinate basis, and it's related to first derivatives of the metric. So there's a complicated formula which I won't put up that relates those. You can look that up. Okay, it turns out that there's another way of writing this equation which is maybe a little bit more appealing, and that is this. Hopefully I've got this right. Okay, which directly relates the change in the index down or covariant form of the four velocity to first derivatives of the metric. Okay, and this is very nice because it immediately allows us to draw some interesting conclusions. So one of the conclusions is that if there's some coordinate that the metric doesn't depend on at all, then the index down component of the four velocity associated with that coordinate is conserved, right? So as an example, in the Kerr metric, the Kerr metric does not depend on the coordinate phi, the longitude. And so du phi d tau is equal to minus a half del phi g alpha beta, u alpha u beta. And that's 0 because this is 0. So this is a constant. Okay, and I'll just say that this constant is the angular momentum per unit mass. So usually when there are symmetries in a system, we associate those with conserved quantities. And in this case, the symmetry associated with rotating the system in phi gives rise to a conserved angular momentum. Okay, so this is usually written u phi is equal to L, where L is the angular momentum per unit mass. The Kerr metric is also stationary, so it doesn't depend on time. And that means there's another conserved quantity associated with that symmetry. And that's u sub t. And the conserved quantity that's usually associated with time translation symmetry is the energy. And we usually write this way. U sub t is minus E, where E is the so-called energy at infinity. And this quantity, this energy that appears here, includes everything. It includes the rest mass energy. So at infinity, for an object that's moving very slowly, this energy is 1. It includes kinetic energy, or what becomes kinetic energy in the Newtonian limit, and it includes gravitational binding energy. Okay, so it's all buried in there through the metric. Okay, so this is an exercise for the students. Expand this in the Newtonian limit. Okay. All right, so next up, I wanted to say a few words about orbits and I'm going to look at the specific case of the angular momentum A is equal to 0, because that will let me do this calculation without filling several chalkboards. So that's a Schwarzschild black hole spin 0. And I want to do this in Boyer-Lindquist coordinates. So you'll see that there are 2 metrics up here. One is Boyer-Lindquist, which is the metric, the coordinates for the Kerr metric that you learn when you open MTW. The lower one is the Kerr-Schild form of the Kerr metric. And this is related to the ingoing Eddington-Finkelstein coordinates that Lewis talked about. And it has the nice property that it's non-singular on the horizon. So this is singular on the event horizon. So this quantity D that appears here becomes 0 on the event horizon in the Boyer-Lindquist case. None of these terms diverge on the horizon in the Kerr-Schild case. So this is up here because it's convenient. The R and theta coordinates are the same as Boyer-Lindquist, but we have different time and different phi coordinates. And that makes it, because it's non-singular, it makes it convenient for studying black holes numerically, because one can integrate gas flow right in through the event horizon. Okay, but for now, I want to just talk about Boyer-Lindquist. And then go to the limit that spin is 0. Okay, so there are 2 conserved quantities here. There's angular momentum per unit mass and an energy per unit mass, E and L, which I had written down and just erased. And I want to make a couple of observations. So first, U mu is equal to minus E, U lower R. And then we're going to consider orbits that lie in the equatorial plane of the metric. So theta is pi over 2. Okay, so U sub theta is 0. And then there's an angular momentum. Okay. And second, I want to observe that I can write UR, which is d squared, dr d tau, is equal to, because of the special form of Schwarzschild, is equal to U lower R times 1 minus 2 over R. Okay, so if I know the coordinate, I can go back and forth between index down and index up. All right, let me explain where I'm going here with this calculation. So what we're going to do is use the normalization of 4 velocities to write what looks like a radial equation of motion for each particle. And what we're going to wind up with is something like a radial energy of motion. So there's a kinetic energy of radial motion and then an effective potential at a given energy and angular momentum. And this will allow us to find where the innermost stable circular orbit is and make some other deductions about orbits in this equatorial plane. Okay, so what I'm going to do is use this condition. And so this is equal to u mu g mu nu u nu. And then I'm going to substitute this for this. And there's a little calculation there. I'm not going to do it for you on the board, but the outcome looks like this. With a little bit of manipulation and rearrangement, I have okay, so you'll notice this is 1 over r. I'm using units such that gm and c are 1. Okay, so this is radius in units of rg. Plus L squared over 2r squared, 1 minus 2 over r. And this is equal to 0. Okay, so you can just, so this is an exercise for the student to go from there to there. There's no thought involved, just calculation. Okay, so this looks like 1/2 r dot squared plus v of r is equal to 0. Okay, so this is an effective potential for radial motion. And if we ignored this term here, which is the only new term introduced in Schwarzschild by general relativity, then this would be an absolutely standard equation from classical mechanics. So there's a gravitational potential here, and then there's a centrifugal barrier here. Okay, and you know, in classical mechanics, this would look like this. Okay, so there's a 1 over r piece here, and there's an L squared over 2r squared piece here. So there's the centrifugal barrier. And if I released a particle here, it would oscillate around like this. And the circular orbits would be right here. Okay. Okay, so there's a new term here, which is this, which is poetically described in MTW as the pit in the potential. People know what I'm talking about, MTW, Meissner, Thorne, and Wheeler. The self-gravitating textbook. Yeah, okay. Okay, so what this new term does is turn this over and turn it down like that. So it goes to minus infinity at r is 0. Okay, so evidently there are 2 circular orbits here, here, and here. This gives us what the orbits look like in Schwarzschild. Okay, so I think in view of the time, I'm not going to work out the orbits, but one can work out the circular orbits from this by setting r dot is equal to 0. And what you find from that is that d phi d tau over dt d tau, which is an orbital frequency as seen by an observer at infinity, is equal to 1 over r to the 3/2, which is exactly the Newtonian result. Okay, now if I were to turn back on all the additional terms, this would change it just a little. So it would go from 1 over r to the 3/2 to 1 over r to the 3/2 plus a. Okay, so final thing I want to do here is ask what happens as we lower the specific angular momentum and bring the circular orbit closer and closer into the event horizon. Okay, so as we do that, this effective potential goes like this, for lower angular momentum, actually not exactly like this, so it goes like this. So the circular orbit moves in as I turn down L squared, and then eventually it flattens off. So there's a point in the potential where there's a singular circular orbit, both circular orbits join together, and this circular orbit is marginally stable. So this is known as the innermost stable circular orbit, or ISCO. Okay. And by taking first and second derivatives of this effective potential, you can find where the circular orbits are, and then you can ask where the circular orbit has a second derivative of the effective potential that's 0. So both the first and second derivatives are 0. That's the innermost stable circular orbit. That's what happens right here. Okay, and then one can solve for the location of the innermost stable circular orbit, and that gives r is equal to 6 for spin 0. Okay. So what I'm going to do, again, in the material that I'll provide with the lecture, you'll find another Mathematica script which calculates the innermost stable circular orbit for any spin. And this is a calculation that was first worked out in nice form by Bardeen, Press, and Tukolsky in 1973. And that's the innermost stable circular orbit is important because we think it's the last place where matter can dwell on circular orbits close to the black hole. So in the classical accretion disk theories, the accretion disk extends down to the innermost stable circular orbit, and then one imagines that matter just flows into the black hole from there, just plunges into the black hole from inside the ISCO. Okay, so we talked about efficiency earlier. So someone asked, I think it was you, asked where the 0.1 came from. And that comes from the properties of these innermost stable circular orbits. So it turns out that we can also calculate E for the innermost stable circular orbit. So we know what the radius is. We know what the angular momentum is from the calculation I just described but didn't do. And then we can plug that in and find what the energy is on the innermost stable circular orbit. Okay. So E goes to 1 as r goes to infinity. So that means that when you're far from the black hole in a circular orbit, almost all the energy is in the form of the rest mass of the particle. And then as you bring a particle down through one imagines a succession of nearly circular orbits to the ISCO, one has to radiate away energy. And so the amount of energy that's radiated away per unit mass is 1 minus E on the ISCO. And so this is the efficiency of a classical thin disk model. Okay, and actually I'm going to show you this right now. I'll make a plot of this. Maybe. There we go. No. I'm looking for a place where I can grab this. There. Okay, good. Okay, so I'm one of the last human beings on Earth who uses command line Mathematica. But I don't program in Fortran 66, though. Okay, so I have a file for you called ISCO. Can you see this? Oh, good. Okay. So this shows this quantity, 1 minus the energy on the ISCO, which is nominally the efficiency of an accreting black hole, the fraction of the rest mass that's radiated away on the way into the ISCO. And this shows the efficiency as a function of black hole spin on this axis. So spin goes from -1, so this is a retrograde orbits, to +1, which corresponds to prograde orbits. And you can see at spin 0, the efficiency is about 0.6, and then the efficiency climbs steeply on prograde orbits because the innermost stable circular orbit goes in toward the event horizon and deeper in the gravitational potential. Contrary-wise, for retrograde orbits, the ISCO goes out. It moves out to 9m for a maximally spinning black hole with retrograde orbits, and the efficiency is correspondingly reduced because you're further out in the potential. Okay. Where's my keynote? Nope, that's the wrong one. Mm. Okay, we'll do this. Ah. Okay, so all right, so next topic is classical accretion models for black holes. So here I'm going to talk about 3 basic models. And the first one is Bondi accretion, which is just spherically symmetric accretion. And I'm actually going to do this in a little bit of detail. So this may be appropriate for modeling some physical systems when the angular momentum of gas that's falling into the black hole is very, very low. It's also commonly used in the literature. So people who do cosmological simulations with active galactic nuclei in them will often use the Bondi rate to estimate the luminosity of the black hole, and it then goes into their feedback models. Although oftentimes they have to multiply the Bondi rate by a factor of 100 to get suitably luminous AGNs. Okay, so spherically symmetric accretion is Bondi. Okay, so that means that del T, it's steady, del theta, del phi are all 0. And we're going to work through an example, which is isothermal accretion. And this is, we can get this by a technique that can be used for other more difficult problems because the flow is completely integrable. There are as many constants of the flow as there are dependent variables. And so this can be used for accretion solutions, wind solutions. So for example, classical model of the solar wind is Weber-Davis model, and the derivation of Weber-Davis model proceeds essentially on exactly the same lines. There's a list of conserved quantities associated with flow, conserved in the sense that they're independent of radius, and the number of conserved quantities is equal to the number of dependent variables. Okay, so in this case, we're going to consider isothermal accretion. So that means that the equation of state is P is CS squared rho, where CS is the sound speed, which is a constant. And we're going to assume that far from the accreting object, as R goes to infinity, rho goes to a constant, and VR goes to 0. Those are the boundary conditions. Okay, now mass conservation. So we have two equations here. We have mass conservation, which gives us partial rho, partial t, plus 1 over r squared is equal to 0, and partial t is 0. And all these things that I didn't write down here, which are related to angular derivatives, are also 0. And so this is our conservation equation. And this is an accretion rate per steradian. Okay, so what we're going to do, since this is independent of radius, we're going to write m dot is 4 pi r squared rho VR. Okay, so there's our first conserved quantity. Next, we have radial momentum equation. Okay, so that's partial VR, partial t, plus VR, r. Okay, plus other stuff. Partial t is 0, and the pressure is rho CS squared. So I can rewrite this, bringing these terms over to the other side, as VR del R plus 1 on rho partial r of rho CS squared minus GM over r squared, plus GM over r squared is equal to 0. And then I can adjust this and recast it as sort of a Bernoulli parameter. Okay, so a Bernoulli parameter is sort of a conserved energy per unit mass. So I can rewrite this as partial r of 1/2 VR squared plus CS squared log rho minus GM over R is equal to 0. So there's another conserved quantity. You can't stop me from doing this. So it looks like an energy. There's a kinetic energy there. There's a potential energy there. And then this thing is the isothermal equivalent of the enthalpy. Okay, so now we have two conserved quantities, and we have two variables that describe the flow, the density and the radial velocity. So we have enough to integrate everything. And what I'm going to do is take this thing. I'm going to Okay, so I'm going to take that thing, 1/2 VR squared plus CS squared log rho minus GM over R. And we know this is constant and independent of radius. And we also know the boundary condition, which is that as we go to large radius, where GM over R vanishes, then the velocity, you have a question?
When you're talking about enthalpy, is that the same as the term range?
No, not quite. They're closely related. So enthalpy, should I talk about this? I guess I can. So fluid equations contain this term, and where this is some gradient. And if P is equal to P of rho, okay, which is true for an adiabatic gamma law gas, or for an isothermal fluid, or in general for what's called a barotropic equation of state, then you can take this, you can integrate this, and this becomes del H, where H is the enthalpy. Okay, so that's what it is. It's not the internal energy. For gamma law gas, it's CS squared over gamma minus 1. And by gamma law, I mean it obeys the following equation of state. Pressure is gamma minus 1 times the internal energy per unit volume. And I'm using a slightly different notation than I think a lot of people have used here. A lot of people use this as uppercase E. Okay. Or treat that as uppercase E. Does that answer your... Okay. Okay, so I can evaluate this at large radius. So this goes away, and this goes away by our boundary conditions. And so it's permanently lost. It's been accreted by the black hole. So at infinity, this is going to go to CS squared log rho infinity. Okay, so I know what the constant is. Okay, and I'm going to call this phi. All right, so the what I can do is take m dot. So m dot depends on radius, density, and radial velocity. And I can use it to eliminate density in this expression. Okay, so that gives me rho is equal to m dot over 4 pi r squared VR. Substitute that in here. Okay, so this is 1/2 VR squared plus CS squared log m dot over 4 pi r squared VR minus GM over R. Okay. And this thing now depends on radius and radial velocity. Okay, so I'm going to plot level surfaces of this. And this is an exercise for the student to carry this through. But what you find is that the level surfaces look like this. So R is on the bottom axis. VR is on this axis. And I'm going to call this absolute value of VR because the sign of VR doesn't matter here. And the level surfaces look like this. And the solutions are all level surfaces of this function because it's a constant throughout the flow. Okay, so if we want a flow that goes from infinity, where the radial velocity is 0, to r is equal to 0, where the velocity diverges, then I have to pick out this one. And it has to pass through this point, which is a saddle point of this function. Okay, yeah. Sorry, yes, that is an m dot. Yeah, so I eliminated the second variable using this conserved quantity. Okay, so now I can basically solve the problem by evaluating conditions at the saddle point. So I can require that del phi del r is equal to 0, and you can work this out. This gives gm over r squared minus 2cs squared over r at the saddle point. So, so that implies that that critical radius is 1/2 gm over cs squared. Okay. And del phi del VR is equal to 0 gives you VR minus, I don't trust myself to do these derivatives on the board. So I worked it out ahead of time. Gives you this, which implies VR, this critical point squared, is CS squared. So this saddle point corresponds to the sonic point, or critical point of the flow, where the ingoing speed is equal to the sound speed. So it has the same form as the radius of is RG. So it's GM over a square of a characteristic speed. And there's an interpretation of this in terms of a sound horizon. So inside this radius, sound waves cannot escape, just as inside the event horizon, light cannot escape. Okay. Now the final step here is to take these things and use them to evaluate this side. Okay, and then I can solve for m dot. Okay, so if I do that, but by the way, I should say this is the Bondi solution down here, and this is the Parker solution for the solar wind up here. Okay, so that's something that starts at low speed, goes through a sonic point, and then goes to high speed at infinity. Okay, and then these things are sad because they're double valued, as are these. These are so-called breeze solutions. Okay, so this thing, I'm not sure what that is. It starts off fast and ends up fast and never goes subsonic. I can't really think of an application for it. Those are the so-called breeze solutions. So those, you can think of those or settling solutions if it's ingoing. So those never go supersonic. So the whole flow is in causal contact throughout. Sorry, Bondi. Oh, you mean do this? I think you have to be continuous and yeah, and the derivatives as well. Okay. So again, I can take these, substitute in here, and solve for m dot, and that gives the following. Okay, so Bondi rate always looks like this. It's got the dimensions of an accretion rate. And so you form that by taking 4 pi times the characteristic radius squared, and the characteristic radius is gm over cs squared, times the characteristic speed, which is the sound speed, times the characteristic density, which is the density at infinity. And then there's this thing out front, which is what came out of this whole analysis. This is an eigenvalue of the problem that arises because I chose an isothermal fluid. So you can do a gamma law gas and you get a different thing out front, which is a complicated function of gamma, yeah.
Relative to the Eddington rate, is this larger?
It depends. It depends on what CS is and what rho infinity is. I actually had a few numbers worked out, but I didn't bring them in. So I'm hesitant to just invent them on the spot. I think um, for 10 to the 8 solar mass black hole, so let me try and pull down something that I remember. For 10 to the 8 solar mass black hole with a sound speed of 100 kilometers per second, which would be hot X-ray emitting gas in the vicinity of the central black hole, and a density of order of few, one would get close to Eddington. Yeah. E is the base of the natural logarithms. Yeah. So that's a pure number. Yeah. Sorry. I used E before, it's the energy. So there's no, yeah, that's not involved here. Yeah. Notational overload. Yeah. Yeah, that's a great question. Um, so I think it's one of the basic unsolved problems in accretion theory. What happens when you throw more gas onto a black hole than the Eddington rate? It may be that in some circumstances it can still accrete, but the naive expectation that I think uh, I learned when I was a graduate student is that once you start trying to do that, radiation just blows all the accreting matter away until it's sub-Eddington. So that's basically the radiative feedback is so strong that it's difficult at any rate to accrete more rapidly than Eddington. Oh yeah, oh yeah. Yeah, so Yanfei Zhang, for example, who's going to be around, is he on Monday? Okay. Um, has looked at super Eddington accretion through a disk. Um, and yeah, it seems to, I, I think that area is still a little bit unsettled, but there's some material that's blown away and there's some that still accretes. I don't know. Yeah. There's a question there of the boundary conditions that I think is important. So yeah, I just leave it at that. So Eddington uses the Thomson cross-section, which means that it envisages the interaction between the radiation and the matter as occurring through Thomson scattering. And actually, you know, gas can have higher opacity than that. For example, the gas around O stars that's in their wind can have much higher effective opacity. So electron scattering opacity is sort of a lower limit on the opacity, and you can actually turn gas around that's cool and has lots of lines, or for example, is dusty at even lower accretion rates. Yeah.
So in accretion disks, the condition of spherical symmetry is often like violated. So why the Eddington limit is still a good indicator?
Yeah, I think that's a reasonable question. Look, there's been a lot of thought gone into um, how to violate the Eddington limit, and I sort of don't want to go into that today. So it's not spherically symmetric, right? And it may not even be axisymmetric. And so if you have a non-spherically symmetric flow like a disk, you can violate the Eddington by some factor that Sunyaev worked out in the 1970s. So you can get stuff to come off the disk and turn around at large radius. Um, and then you can also change the mean molecular weight. So if you're accreting mostly helium, as we think may be the case in the center of our galaxy, central black hole may be accreting mostly helium because the gas supply is from wind-losing, mass-losing stars that are orbiting the central black hole. Then the Eddington rate goes up again. Yeah, so there's been some work done on stability of so linear stability of the solution. Actually, that was what I did for my undergraduate senior thesis, I'm embarrassed to say. Uh, and it seems to be stable, but that may depend on the equation of state. If you have an angular momentum per unit mass that produces a circularization radius that's outside the central object, then you can expect that a sort of a disk will form close to the central object. If a circularization radius is outside the boundary radius, then this is probably not a good model, at the very least. Okay. I have 3 more minutes before lunch, right? If that. Okay, so I have 2 more accretion models to go through. So one is geometrically thin, optically thick disks, which are also known as alpha disk models or Shakur-Sunyaev disk models or Nabokov-Thorne models, variously. So I'll do a little bit on that after lunch. One of the notions in that work is that there's turbulence in the disk, and that the turbulence can be modeled using viscosity. And so I'll also talk briefly about that. But let me just show you an animation. So this should wake you up before you go to lunch. An animation similar to what Phil showed of the development of turbulence in a disk. Okay, so this should motivate some of what I talk about later on. This is a stratified local model of a disk. So we take a little box and allow it to orbit with the plasma in the disk and impose boundary conditions that are nearly periodic in radius. And then this particular model extends over several scale heights of the disk. So it's thicker than the disk itself. We put a little field in the initial conditions, turn it loose, and it develops into turbulence, and the turbulence produces a stress that transports angular momentum outwards. And in this case, the turbulence is driven by the magnetorotational instability, which was brought into accretion disk theory by Balbus and Hawley. Okay, so this is either the finest simulation of this problem that's ever been done, or a colossal waste of computer time. So what this shows is a very high resolution model of an isothermal disk. So P is CS squared rho. And it's a so-called ILS model, or implicit large eddy simulation. So there's no explicit dissipation. There's no resistivity. There's no viscosity. All the dissipation is handled by the numerical scheme. And because it's a conservative scheme, well, actually, this is isothermal, so I shouldn't even say that. But it's all the dissipation is handled by the numerical scheme at the grid scale. Okay, so there's one of the major computational problems here is whether we should even be doing simulations like this. I think Keaton might say no. Some people would argue that now we have sufficient resolution to do simulations with explicit dissipation models. But we can talk about that later. Okay, so that's it for lunch, before lunch.